welcome to Ladyada.
Hey everybody, and welcome back to my desk where we're doing a bunch of electronics this week. But first, we have a message from our sponsor.
No. I don't think Little Tykes and IBM is going to sponsor us, but they should. We have this neat thing that we did, trying to do. I've been looking for a way for you to... we have a daughter, so we want to have her learn computers from the beginning, so it's not just a rectangle slab that is used to purchase things and pay for subscription services. So a million years ago, Little Tykes and IBM, actually 1998, did a thing called Young Explorer. And this is what the box looked like. And it was an IBM and Little Tykes team up. Now it would be like Little Tykes X IBM. And it's a computer station from 1998, and it ran, Windows, and it was like basically a really great PC case. We have one. So the plan is, here's our kiddo. We don't really show her face, but we can show her from this side. Our plan is to go through the history of computing and have it so she learns computers one computer at a time. And I was inspired by, Andy Bio did this thing with his kid where he did video games like that. And the video games were, some of the older ones to, more recent. So that was kind of neat. So there'd be an Altair, an Apple I, a Commodore PET. There would be an Atari 400, 800, a Commodore VIC, an IBM PC, a Commodore 64, Apple Mac from 1984, Amiga 500, Next Computer, SunSpark Station, Compaq, Sony, Apple Mac, Dell Dimension, and then other ones because I'm like, hey, social media, what do you think? TRS-80, Sinclair, Acorn, BOS, Silicon Graphics, and then, there's some other stuff like Prodigy and eWorld and AOL. So, Ladyada, what were the computers that got you started and that you're going to put in here for her to learn?
Well, to be honest, when I was in school, we had Apple IIe's and then Apple IIgs's. So there's a lot of, number munchers and... let's see what else. It was like there's some pond, there's some lake-based game, and then Oregon Trail type stuff.
Okay.
And then
so you're allowed to play Oregon Trail.
Yeah.
What else?
And then I just love those diskettes. You have to put the diskette in.
Yeah. So we're gonna try to do some of the real physical hardware, but when we can't, we'll emulate. But this is a good start. So each one is
we have an Apple II kit. I actually just got my clear Mac Effects Apple II case. So we're going to make the Apple II. We have an Apple II. I don't know if it's Apple IIe or Apple II. I think it was an Apple IIe. Maybe it was a 2GS. They got a clear case, and we have the clear floppy drive. So we're set. And then we had a Mac Plus, which I totally loved. I just loved that Mac Plus. And then Mac SE30, which was like the best computer ever made. It's all been downhill since System 7 won. And then I had a Quadra 650. No, it was a Centra 650. But I hand updated it to a Quadra by popping the chip out. It had the 68040 LC, and I upgraded it to the 68040 after a couple of years. I had a floating point unit. Which is amazing, at the time, computers did not have floating point units. But that was a great computer. It had a color screen and everything. Yeah. And then I think from then... I had to kind of go into Windows land, so I had a Pentium and stuff, because I want to use Linux.
We'll use Windows 3.1. We'll have Windows 98, Windows XP.
Yeah.
I feel like...
We did that video, that guy who updates, he installs Windows 1 and then updates it to Windows 2, and he does the update process all the way through. And he actually got all the way to Windows 11. Something stopped working, but he's I think he had it's a color scheme, and he's the color scheme actually got updated all the way.
Yeah, there was something that made it all the way through. It's it
was a calendar or
yeah, we'll check that out. Someone in the chat will probably put a link. So anyways, that's our plan.
Awesome.
Yeah, so that's our plan. Yeah. And she's young. So we have plenty of time for this project, but we have all these computers for our museum that we're doing in Adafruit. So I'm like, well, here's this stuff that we can do, and it'll just teach computing in a way that I think that we're all used to, which is it came from something else that you had a better insight on how it worked. So anyways, that's our project.
Okay, so you put that together this week.
Yeah.
I think to start we might actually just go with what did you Photoshop onto here? We're gonna start with maybe we'll do Noah and Pedro's project where he like just plays little videos where we have the cards. And then,
Yeah.
You know, she gets like 3 cards a day or something. She can play like three short videos or something.
Yeah. Okay. All right. So let's get on to Desk of Ladyada. What's on your desk this week?
Speaking of retro stuff, let's go to the overhead. I got my Floppsy Rev B PCBs. I'll admit I have not even brought them up. All I did was make sure that they enumerated, and I sent Jepler some because Jepler had time this week and I didn't. But today's my day to go work on Flopsy. Still's got the RP2040, but now, first off, I wired up the level shifter so it can be both in emulation mode and reading mode. So it not only can read from a floppy drive, but it can emulate a floppy drive, which I think is really cool because there's not a lot. I don't know of any boards that can do both. This is a 12 volt power supply. I added a 12 volt buck supply here, negative 12 volt buck supply. So this is 12 volts in, because I don't want to boost from 5 volt to 12 volt. That's like 1 amp, that's a lot. I think it's better just to say, hey, you guys need 12 volts in. And now that we have those USB-C to DC adapter cables, it's like you can just power this from USB-C. You've got the buck converter from 12 volt to 5 volt, but then here this is a negative converter that will convert from 5 volt to negative 12, and you need that because the Apple Disc 2 has a negative 12 volt rail, and it's not used for power. It's not used for the steppers. The steppers are driven from 12 volts. It's used for like the biasing circuit, and basically historically when you had power supplies you'd have a transformer, and so you would get like negative 12 volts for free. And so he Woz used that for the tuning circuit. I don't remember, but I remember looking at the schematic and being like, oh, okay, this isn't like a high current thing. Added the 2 sensor slots because for the Apple II there's no index sensor, but you can DIY an index sensor very easily. So these are 2 power, ground, and signal input. There's 2 of these. And I added up, down, left, right buttons for the TFT interface and a GPIO expander, which I totally kind of messed up. And the boot pin, I wired into the expander and I shouldn't have. So I'm actually going to take it out and I'm going to cut it and like wire it to I think we have like 1 or 2 extra GPIO on the RP2040. Maybe I'll wire it there. I still got the debug port. White protect is a physical switch. And I just fixed up a couple little things here. So there's still a couple of mistakes. One thing is I forgot for emulation mode, I need to have pull-ups on here. So I'm going to add, I think just like 2.2K. I think there'll be plenty, maybe even like 3K pull-ups on these lines. So it'll be kind of weak. Definitely like this will be able to overpower it if you happen to like have things going the wrong direction. But not harmful to have a couple extra pull-ups. So yeah, it's like TTL logic. It was all open drain. So hopefully I'll get that up and running soon. Got the little happy sleeping bunny on the back. But yeah, a lot more space got taken up, which is good because this is like floppy. This is actually floppy disk sized. Okay. Next up, I also tested and validated my BQ25185 designs, which y'all might remember from a few weeks ago. It was actually kind of sunny here in New York, so I was able to wire up a solar panel. And it actually worked quite well. This actually does great solar, not max power point, but max voltage current input. It's not max power point because it's not a switching converter, but it is optimized for solar. You'll get very good solar performance. And for a chip that's like $1, that's great. You know, a max power point converter usually is quite expensive. So 2 versions. This version, so I actually made a couple changes I'll show on the overhead when I get there, to this to make it work with lithium ferric phosphate batteries easier, and also to change the current rate a little bit. So you can have, by default, 1 amp charge, but you can also have like a half an amp if you want. Has some LEDs, just breakouts. It's just a kind of nice like all-in-one BQ25185 dev board. So I kind of did a couple changes, but most of this was ready to go. And then this is the buck converter version. So it's got the same charger chip here, and then some breakout pads. and 3 volt output. I think I made a couple small changes to this too. Did I make? Oh wait, hold on. Actually, sorry, this is the original version. I don't know if I have the other version. The other version, well, I'll show it. But basically, I made a version with the BQ 185, and this worked quite well too. Gave me about like 1 amp at 3 volts output, but switching, so it's a little bit more efficient. So, you know, especially if you're doing solar power, you want to optimize your 3 volt output. Okay, can we go to the computer? I get some tea in me. So with that done, I wanted to do a version that had a boost converter. So this version has the USB-C come into the BQ 185 as normal, battery charging here, and then this has a boost converter. The output of the BQ 185, let me see where it is. Okay, it has a VSys output, so it has a load output that is regulated. So this output VSys will never be higher than 4.5 volts, which is actually quite handy because this chip can actually handle like 16 volts input, which is actually a little stupid because it overheats very quickly because all linear. So you give it like, you know, VN. I put in these 2 very low forward voltage diodes for VN or VBus. VBus is from USB, VN is from solar or DC or whatever. And if it's a 6 volt, I would always recommend a 6 volt cell, maybe even a 7 volt cell at the most. But this will never, the goal here is just to make sure VSys never goes above. And when you do other load sharing, sometimes it just gives you whatever the V input is. And so it could end up being, you end up having to do a buck boost if you want 5 volts out, because it's like, oh, if the battery's charged, the solar cell will float up to 6 or 7 volts, and then you're kind of out of luck. So what's nice is that it's not as efficient because it's linear, but at least you get 4.5 in here. And then here's my little booster. This will give me 1 amp easily, maybe up to 1.5 amps if the battery is charged quite well. It doesn't, you know, it's a kind of, I think of it sort of as a solar friendly replacement for the Power Boost 1000, because this will charge at a 1 amp rate. It has load sharing, 5 volt, 1 amp output, but a lot less expensive, more like a lot more optimized than the Power Boost, and the load sharing is I think a little bit, it's not, it doesn't do 1.5 amps like the MCP, but like the cost is going to be very affordable. And to be honest, not a lot of people need a huge amount of current for driving their project. So basically, I'll have a version with 3.3 volt buck output, 5 volt boost output, and then, you know, this will be a good way to experiment with this chip. Okay, so that's the BQ 185. Next up, oh, as I did the Floppy driver, you know, remember I said I needed that negative 12 volts, and it's actually like kind of hard to find a negative 12 volt chip. I'm not going to go for the great search this week because I have another thing I'm looking for, but maybe next week I'll show how I found this chip, because all the other negative 12 volt power supply buck converters, 5 to negative 12, were really expensive. You know, there were a couple that weren't too bad, but it was like easily like $2. And I was like, I really don't want to spend $2 of my BOM on a negative 12 volt supply. And it was a little annoying because I was like, oh, you know what, maybe I should use like a max 232 to get, you know, again, you don't only need like, you know, 20 milliamps. But I wanted the stability. The problem with the max 232 is it's doubling. So usually you get like 5 to negative 5 to negative 10. It's not guaranteed to actually give you negative 12. And I wanted that negative rail to be consistent, because if you're tuning your floppy drive, like, you want to have the same voltage each time. You don't want to have to be like, oh, you know, it dipped or it raised, you know, based on the 5 volt. And especially when the motor kicks in and then it maybe fluctuates, I wanted to be a little more stable. So the TPS 65131, I was like, oh, you know, this is kind of a handy board to have. It's like, it's so rare to find ways to get a true split supply output for circuits. Like, it's easy to get something that boosts to 5, boosts to 12, boosts to 10, or whatever. You're adjustable. Once in a while you can get inverters, but it's really unusual to get something that can give you a split. And you might want to split when you're doing a lot of like synthesizer stuff or analog. I took like analog lab, and we were constantly needing plus or minus 12 for our op amp designs or our, whatever, filters, motor things, whatever. So this will give you plus minus, well, actually it's interesting. It'll give you plus or minus 6 to 15. So I put little trim pots on there, and you can adjust it. I figure, like, usually I don't have adjustable for power supplies, but there's times you want plus minus 6, plus minus 8, plus minus 10, plus minus 12, or plus minus 15. Also has like a Heath kit stuff. Like, I remember it has a lot of, they often have negative supplies, again, because when you have a transformer, it's easy to get a split supply out. So this is the split supply buck boost. You give it 3 to 5 volts in, and it'll give you negative plus minus. Not a huge amount of current, maybe like 100 milliamps, maybe 200. I'll test it out, of course. But, again, it's like such a pain to get split supplies that I think this will make some people very happy. Okay, so let's go to the Great Search.
Where in the world is that part I need? The Great Search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Thank you so much, DigiKey. Every single week, Ladyada user-powered adventure, you find things you want and need. You cannot be found unless you're lost. Ladyada's going to find you.
Oh, you know what? Hold on.
After she does.
I just realized my display is set to 720, so let me boost it to
Boost it.
1080.
Boost it.
Let me boost it to 720.
Press the boost button.
Okay, boost. We're boosted. Okay, thanks.
All right.
It's a little easier to see the UI and the text. Okay,
Okay.
as you were saying.
No, that's it.
That's it? Okay.
That was my intro.
Thanks.
We're here.
Okay, so we had a couple requests this week to carry more stepper drivers at Adafruit, and I will totally admit that they're right. We don't really stock a lot of stepper drivers. We have like breakout boards for like the TB6612 or DRV8833, and these are boards that you can use to drive steppers, but they don't do micro stepping automatically. Like, you'd have to use PWM. And there's a lot of these like all-in-one little driver chips that Pololu especially has like done an excellent job just kind of creating these standardized breakouts that are used in almost every 3D printer and CNC project, where you have these little boards that you can pop in and out with your favorite stepper. And we actually even covered, one of these kinds of stepper drivers on INPI, the Trinamic micro, like silent step silent micro blah 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 step thing. So using this configuration interface, MS1, spread, PDNU, whatever, and then step endure. And what's really nice about these is once you set up the configuration, the direction pin, high or low, is forward or back, and then you just toggle step, and it does the micro step. And it's like, that's it. It does everything. It does the current management, it does the micro stepping management, it counts, it integrates, it does your dishes. They're amazing. They're a little more expensive, but they're really, really easy. And what's nice is, you can even drive them from something like a Raspberry Pi. You don't need real-time control, because as long as you just toggle the step, and even the slowest single board computer with like the biggest delay, it's not going to be more than like 10, 30 milliseconds. It'll be just fine. So there's a whole family of these, and I don't know what the first one that came out with, but we did a design for like the A4983, and even this was kind of late. This was a stepper driver design that K-Town did back when he was doing designs with us, and he kind of followed the layout. It's kind of a chunky board, but it has this chip in the middle, and then you can control it with the micro stepping setup, ground, enable, reset, sleep, dur, step, and power. And so I thought, I'd also design a board for kind of like the most popular, not the best, but the most popular of the series, the 4988, which is the update for the 4983. This one really kind of like nailed it a little bit. This again is used in just like virtually every low cost CNC 3D printing, stepping, driving thing. You have the 3 control pins, reset, sleep, enable, during step. And then for me, I actually had the, for this board, I have the power, the motor power input here, and the 4 control outputs. And this is going to be terminal blocks, although I might make a version that has like, you know, a plug-in as well. Happy with this and stuff, but there's one downside for the A4988, which is that it is, let's look it up, A4988. I think the minimum voltage, I mean, like, there's like 25,000 stocks. So you can see this is quite a popular chip over at DigiKey. The logic can be 3 or 5 volts, and it's amazing capacity, up to 2 amps per drive, per leg. But the voltage for the motor, I believe, is 8 volts minimum. Yeah. Load supply voltage range 8 to 35, which is great because it covers like the most popular 12 volts that we've seen, and I've also seen 24 volt motors. But we do have some motors that we stock, like little mini steppers that are 5 volt. They actually are limited, like you really don't want to drive them at a higher voltage range, even if you're like, I mean, I guess you could current limit them, but still, like you want to drive it off of 5 volts because you have a lot of 5 volts around. So I wanted to find something on DigiKey that was, had the same kind of like concept where you have the step select and then reset, enable, sleep, and then step and direction and bipolar output, but can do 3 or 5 volt logic for the signals, which is very common. I'm not worried about that, but can do down to 5 volts, but as high as 12. So I want it to like be a little, it doesn't go up to 35. I just want it to be at least 12, but down to 5 volts. So let's go. Well, actually, you know, we're here. We can just go to the motor driver controllers category. And there's a lot. There's like 5,000, but we'll start paring them down by only looking for active, and then normally stocking, and I'm going to just exclude the marketplace stuff for now. And that at least gets us down to 1,400. Next up, the motor type. So I don't want it to be a voice coil or piezo driver or brush DC, which is very common. I wanted to do stepper. This is stepper, stepper, and then I'll do universal, although I don't have a lot of hopes for that. But definitely not just brush DC. It should be able to do, because again, I want to do that stepping interface. So let's filter on that, and now we have like 300. So the next up is the function. Well, actually, so, sorry, let's look at the step resolution. Well, so I did want to have it be able to do like more than just one step. I want to do like at least like 1/16 or 1/8. So I selected all of these, and then I took away, like, there was just only a couple, but I figured I'd filter them out. Okay. All right, and then next it was the function. So I was kind of confused about the function, but then when I looked, although, you know, you can see here, it said, I'll say, this says step direction. It's kind of promising. There's so much, like, I kind of ignored the applications because that's a little confusing. Let's look at voltage. So there's voltage supply and then voltage load. Voltage load is the thing that you're going to drive. So again, I want it to go up to 12 volts. So I'm going to ignore this 10 volt one, and I'm going to pick out the ones that are 5 to 12. Looks like there's quite a lot of options. So I'm just option clicking 5, and then I picked up like this one, and I'll do the dash as well. Okay. All right, 95 options. And then I started noticing, oh, there's like a couple that are like this one. And I'm like, oh, the EMC23, I know this. This is a fan control chip. And then driver, I was like, well, what's the difference between driver and driver fully integrated? Driver not integrated is you have to have a separate H bridge, and usually you do that with like in this case it's like a FET or something. So we don't want that. We want something that's like, again, all in one. So let's go back up here, and then we're going to take away fan control, and we're going to take away driver. And then just so you know, I also checked controller commutation and speed. Those are also, they don't actually have like the H bridges built in. We basically want driver fully integrated power control phase. All right, so this gives us like 50 options. And then finally, I don't want through hole. I don't want surface mount. I think there's like one through hole chip. Okay. All right, so now we have a lot of options. Some of these are very familiar. I've seen like the ST Spin series and the DRV88, series, and then those Allegro chips. Those are here, and if you can filter downward by quantity. You'll get, Allegro chips, and then again more ST Spin. But I wanted to actually do by price to start, and there's a couple options that looked appealing. One is the DRV8824 series. This looked pretty good. This is a dual H bridge stepper motor driver, up to 32 microstepping, step control, great. I like this 8 to 14 volt power supply range, 1.4 amp per H bridge, which is great. TI makes very good drivers. It's a little confusing because it looks like, oh, can you give it 3 volt logic? It turns out like if you keep going down, the power supply for the motor is maxed, but there's an internal regulator. And so the control pins, you can give 3 or 5 volt logic. Actually, that's the max, but if you go down to like logic level, so the basically high logic level is between 1.6 and 5.5. So yeah, you can use 3.3 volt or 5 volt logic. So this chip actually looks really good. Also like that I wouldn't be surprised if it was very, it looks very familiar to the layout of the A4988. I wouldn't be surprised if this was like fairly easy to select in. They usually have like sense, they have like, decay setting, micro stepping settings. This is kind of cool. Torque, DAC, scalar. Like they always have these little tweaks that let you, you can have a voltage, but you can have the torque and current limit as well. So I like that. But I also thought this was kind of nice. This is like very inexpensive, which could be good. It's like maybe I should make something very cheap and easy. This is a Toshiba, also available in the QFN, which is great. And it has the control supply, 2.7 to 5.5 volts. Output current is going to be less than the other one. This is only 0.8 amps, but maybe that's okay. And on resistance is, not too bad, about 1.2 ohms. And then micro step controller. So this one's interesting too. I have to look to see if this is the same. I think this is the same configuration. I think CW, CCW, so clockwise, counterclockwise, that's the same as direction. And I think CK is clock, which is like, step. But these two are really good. So I'm going to look into this one a little bit more. It's, just the inexpense of it. I can make a little I2C motor driver board and have maybe like a I2C to step expander, and you can make little chainable motor drivers. So I'm going to take a look at this one. Also check out the TI one, but the TC78S600 series for a direction and step medium voltage stepper driver.
And that is the great search.
Where in the world is that part I need? The great search with DigiKey.
Alrighty, that's our show for today, everybody. Thanks so much for joining us. And online, you can see some of the suggestions folks have for our retro computing station for our kiddo. We'll see what type of systems and more we put on. And we'll see everybody throughout the week.
Thanks, everybody.
Bye-bye.
Bye.